When a new AI model drops, the question that matters for most teams is not just which hardware you own. It is whether your operating system can move data fast enough to make it useful. Many assume modern means, modular or micro-kernel designs are inherently faster for performance. They believe Linux's monolithic kernel is a legacy relic holding back progress. But this assumption is dangerously wrong when dealing with GPU and TPU inference. The specific architectural choice Linus Torvalds defended, the tight coupling of that so-called monolithic design, is actually the only structure capable of handling the microsecond-level latency requirements of modern AI training and serving. If you switch to a more modular OS thinking it will improve your pipelines, you might just break real-time responsiveness entirely due to unavoidable context. Switch overheads. Today we connect this headline to the engineering trade-offs behind the hype, looking at why Linux remains the undisputed king for high-performance computing in 2025 and beyond. The confusion between modern and fast is a trap that misleads many developers. We often equate modern with separation of concerns or microkernels where services run in isolated user space to improve security. While this works well for general-purpose desktops, it creates a fatal bottleneck when streaming massive data volumes directly to specialized AI accelerators like GPUs and TPUs. In these systems, every time the processor has to switch from user mode to kernel mode or pass control between separate modules, there is a cost. Imagine running a race where you have to stop at every meter marker, hand off your baton to a new runner who then hands it back before continuing. That context-switching overhead accumulates rapidly and becomes the limiting factor in low-latency inference. Linux's monolithic kernel avoids this by keeping drivers and memory management logic tightly coupled with the core execution path. This allows for direct memory access optimizations that bypass the traditional handshakes required by modular designs, ensuring data flows from storage to processor without friction. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Recent research validates that this design is not a relic but an active enabler of performance. A 2025 study conducted jointly by TU Munich and Pace University challenges the notion that separating kernel services always improves safety or speed in AI contexts. Their work on composable OS kernels proposes treating loadable kernel modules as high-speed computation units themselves, capable of executing sensory processing and neural inference directly within kernel space. This approach eliminates the latency caused by traditional user kernel context switches, which is fatal for time-critical tasks. By moving the heavy lifting into the core where it belongs, they achieve a level of responsiveness that modular systems simply cannot match without significant architectural changes. The study highlights how this shift transforms what was once seen as a security risk, the large attack surface of a monolithic kernel, into a performance superpower for inference engines that need to react instantly to changing inputs. Beyond raw data movement, the scheduling flexibility provided by Linux's architecture offers another critical advantage for AI workloads. The system leverages an adaptive framework known as SchedX, which allows for what researchers call mixture of schedulers. Instead of forcing a single static policy on all tasks, this system dynamically switches between specialized expert policies based on real-time workload patterns. In testing scenarios involving diverse AI inference needs, this adaptive approach outperformed default Linux scheduling in 86.4% of cases by matching hardware capabilities with task requirements instantly. This means that during periods of high training load or bursty inference requests, the operating system can pivot its strategy without human intervention, ensuring that your GPU remains utilized efficiently rather than sitting idle while waiting for a rigid scheduler to catch up. There is also a significant misconception regarding security and code complexity that needs addressing. Critics often argue that because Linux has grown large over decades of development, it must be harder to secure or patch quickly compared to smaller microkernels. However, analysis from Microsoft Research in 2026 suggests the opposite might be true for modern deployments. Patch latency is driven more by kernel recency than by common vulnerabilities and exposures, severity scores alone. Since Linux moved to become its own CNA in late 2024, vulnerability reporting has increased in order of magnitude, indicating a much larger ecosystem actively hunting for issues rather than hiding them. This transparency allows the project to manage and fix complex monolithic code rapidly when needed, proving that size does not equate to stagnation or insecurity. The community's ability to identify and resolve critical flaws quickly ensures that the platform remains robust, even as it grows more capable of handling next-generation AI workloads. For practitioners designing infrastructure for large language models or real-time computer vision, this architectural reality changes how you evaluate your stack. You are not just selecting hardware like NVIDIA GPUs or Google TPUs. You are implicitly choosing an operating system architecture that can move data without friction. The monolithic kernel provides the tight coupling necessary to bypass overhead in interrupt handling and memory management, a trade-off where raw performance wins over theoretical modularity. As AI moves from static inference to adaptive real-time processing, Linux is evolving into a composable platform rather than abandoning its roots. Developers need to master loadable kernel modules and kernel space optimization as these become standard for high-performance deployment. Understanding this distinction means making better engineering judgments about where your latency budgets are truly spent and ensuring that your software stack aligns with the physical constraints of the hardware you rely on. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.